start recording. Okay, good. So it's great pleasure to have Mauricio Romo from Yonsei Tsinghua. He's going to tell us about the exponential network, BPS, and quivers.
Okay, hello to everybody, and thanks a lot to Satoshi for setting this up and for the invitation. Always a great pleasure to talk, even if also virtually. So today I'm going to talk about some work I did with Banerjee and Longhi. So I will put here the reference. So it's based on the following papers. So one is this one, and the other is this one. Okay, so this is with Banerjee and Longhi. So this is about some kind of generalization of exponential networks. And in advance, I apologize if anybody here have seen some other iteration of this talk. So I've given several iterations of this talk, me and my collaborators as well. So I hope this one at least contains something you can learn, something new if you have seen it before. If not, well, you can also sleep or something. The more or less the plan for this talk will be to give a slight introduction, so the outline. So I will talk about the physics and a bit on the math setup. Mostly on the physics setup and kind of the math consequences first, particularly about the enumerative invariants we can compute with this. Then I will set some generalities, a bit informal, of what are exponential networks, so kind of some definition. And after that definition, I will go for applications. So usually there are two applications so far we have been working on. One application is the something called nonabelianization map. And the other application is this BPS quivers. So the BPS quivers is something some people have asked me to actually talk about. Usually I manage to talk about this one, but not not about the BPS quiver. Never is enough time. So this time when it's the time for applications, I will start with the BPS quivers. Okay. Even though, so the non-abelianization map, the importance I wanted to mention why I always talk more about this one is because the non-abelianization map is the way to connect with enumerative invariants. Okay. So the talk will be a little bit more on the physics side this time. Let me start then with the physics setup. So physics. So what's the setup? So the setup of this story is M theory. M theory on R5 cross X, where for us X will be a toric Calabi-Yau threefold. So it's a very particular type of Calabi-Yau. And we will take actually this R5 actually I will rather take instead of R5, I will rather take immediately whether R4 cross S1 cross X. So I will put that circle there. So the idea is if you have this setup, you have a 5-dimensional theory which is obtained by so-called geometric engineer, which I can call it, if you want, the 5D of X. So it's a gauge theory that lives on this space, on this R cross S1. So one question, the question we answer, the question we want to ultimately answer is, or one of the goals is to count 5D BPS states. Okay, so these BPS states can be of several types. One can come from N2 branes, for example, 2 branes wrapping some S1 cross. So this S1 is exactly this one of before, this one here. So wrapping S1 times some 2-dimensional submanifold. So with some class, let's say beta in here, compact. You can also do non-compact, but we haven't really studied that. Okay, so you can think of this beta just compact to cycle. And these are some kind of BPS states that you can have, that you see. There will be kind of lines on this 5D, so there will be some kind of particles. And also, you can have N5 if you want N5 branes wrapping R cross S1 cross C4. So this is a 4th cycle, but this not today. Not today, because actually this is part of work in progress. All the examples you will find on these papers I showed previously, this one and this one, are actually cases where X is storic, and the Calabi-Yau threefold is Calabi-Yau threefold, so X doesn't have compact 4 cycles. People that are familiar with these stories, this type of story, know the extra difficulty that compact 4 cycles can bring sometimes. So it's not really trivial. I mean, it looks straightforward, but it's something that requires some work. So the examples we have, you will find on those papers, are the ones that doesn't have compact 4 cycles, namely like conifold, or like C3, or these strip geometries, for example. So these are the type of invariants that we are interested in. So mostly these ones. So in particular, we will denote these VPS states are traditional. So these VPS states, the counting of this VPS state, I will denote it like this: omega T0 plus T2 plus T4 plus T6. So this VPS state, upon reduction, you can, oops, I don't know what happened. Upon reduction, you can equate them to bound state of D branes. Okay, so in particular, the ones we are concerned about, and the ones that we compute, for example. So, for example, the ones that we can compute are states that have some D2 brane with some class beta and some K units of momentum along this one. This, you should think of this like this. They can be interpreted after reduction as these 2 brane with bounded with KD0 branes. Okay. So these are some, I'm giving you the results immediately. The results of what we obtain on those papers is that this, for example, we can compare with these ones, these numbers, which are Popa-Kumar-Baffa invariants of genus 0 and class beta. And yes, it doesn't depend on K. We can actually also compute, if you want, K zero brains, and this also doesn't depend on K. This minus here is conventional, and these are all equal to the Euler characteristic of X, defined in an appropriate way, because of course X is non-compact. And I wanted to mention that via wall-crossing formula, this one I will not have time to detail here, but you can also find it on the paper. So these two are computed directly using the exponential network, using the exponential networks and the nonabelianization map. Via word crossing, you can also compute stuff with D6. So we cannot compute directly with D6. We can even compute with several D6. So L larger than 1. So we can compute this kind of states via word crossing. So this, just the reason I'm mentioning this is because you may be familiar. These ones are the usual Donaldson-Thomas invariant with n units of D0 and I don't know what the fuck, and beta, and class beta. And these, I don't know, these are like so-called higher rank, maybe Donaldson-Thomas invariants. They just came up from the word crossing formula. So we don't have much to compare these ones. But these ones are, these ones and these ones are well-known invariants that we can compare with the things that they have been computed before, right, for this Calabi-Yau. So ultimately, the idea was to to compute these 5D BPS states, but in order to compute them, we use kind of similar. We use essentially an analogous of the approach, as I was mentioning, of the spectral networks. So to compute 5D BPS states, we introduce a defect that I will specify in a second, a defect, and relate them with 3D, 5D BPS states. So this is the Gayoto-Moon-Knightsky setup, just kind of lifted to M-theory, where they compute 4D BPS states via 2D, 4D BPS states. So for people that are familiar with that story, that's really the lift of that. And I will tell you now what's the defect, because that will play a role on this definition of the exponential network. I mean, that's kind of the most important part. So what's the defect? So again, remember, we have this setup. Okay, so now you just take here some L, so this is Lagrangian submanifold times, let's see, I don't want to, this is, yeah, times R2 process 1. Okay, so this is some M5 brain. So you just pick one M5 brain with this topology, and that's your defect, okay? The Lagrangian submanifold is not In principle, you can take any Lagrangian submanifold that you want to create this defect, but that will complicate your life too much. So you take a particular toric Lagrangian. So we take, well, I already told you that it's a toric. We take L, some Lagrangians that have like this type of topology, which are known as aganagic buffer branes. Or should I say aganagic? So it's a toric brane. And also aganagic buffer brane. It's because they were defined by, what is that shit? They were defined by aganagic and buffer, some kind of generalization of these branes by Lawson that has this topology. So there is some particular property of these Lagrangians that's actually very important, and the property is that the moduli space of the formation, so the moduli, so let's say this is a fact. So the moduli space of the formations of the A brane, not of L, but the A brane associated to L, so meaning L plus local system on it, or flat bundle, U1 flat bundle, so it's a U1 because it's only a single M5, okay? What the moduli space of the A brane is a curve in, we can write it in C star cross C star, okay? Indeed, is the mirror curve of X. So just for later, I will denote this curve has sigma, and it's defined by some polynomial equation x by 0 inside C star cross C star. So this is typical story for this toric mirror symmetry, and maybe people that are familiar also know, like if you want the mirror of X is given by this, by some conic bundle over this, okay? So this is called the mirror curve, in case you are not very familiar with this story, but you don't need to know anything about mirror symmetry for this talk in principle. However, it gives you a very nice intuition. So that's the curve that define the moduli of the formations of this A brane, and that's actually the curve that will play the role of the, if you want, of the Seiberg-Witten curve of this of the spectral curve, if you want, of the spectral network story, but in our case. Okay. So what's the idea? First, let me just explain you what happened after we introduced this defect. So the idea is, after introduce this defect, we have a 3D theory T of L on R2 cross S1. So you have a 3D theory on the defect, right? We go back. So it's a 3D theory now here. So it's a 3D theory that's coupled, of course, to this 5D theory because of how the L is embedded, etc., etc. So the 3D theory kind of doesn't live a life by itself. It's not very. It sees the 5D theory, right? Somehow. And the idea is that you compute the BPS states on this theory, and they are related to the pure 5D BPS state. So this theory, if you compute this, the BPS state on this theory, these are the 3D, 5D BPS states.
Oh, Mauricio, are you writing?
Yeah, what happened? Your screen sharing is paused.
Is it only my problem? I cannot see.
I can't see either.
Go now.
Somehow,
it says screen sharing. He said I got something that said your screen sharing is paused.
why is that? I'm sorry. I don't know why.
I don't know how. Did I press something? Here it resume share.
Oh, okay. Well, now I think it's okay.
Yeah, sorry.
Okay.
Maybe it was me.
Okay.
Okay, yeah. I'm such an old person now.
Yeah.
Okay, so
please go ahead.
So okay, how I'm doing with time? Oh, okay, I'm doing pretty well with time. So yeah, so this is the curve, and this is the moduli space of that. So that curve will enter soon to the definition of this exponential network. And this 3D theory is what as I mentioned again, this 3D theory is what enters into this 3D 5D BPS state. Like this is the 3D there. So next, yeah.
So hi Mauricio. Is there some intuition and understanding why this Miller manifold of the non-compact Calabi-Yau is same with this modular space of this historical A-brain?
Oh yeah, that's a computation you can do. That's not that's a very old computation if you want. So kind of that goes back to Aganagi Kambafa original paper.
Yeah, I remember. Yeah, is there some okay.
So I don't know if I can provide a quick and short answer, but essentially you write like some you can write, since the brains are toric, you can write kind of like some moment map type equation, like some d terms and quotients that describe the brain.
So it's like this A brain is like a proper brain, and to capture the complex moduli space of the Miller Calabi-Yau.
So it happens because the brains, these are the brains that you can, I mean, they coincide because the position is essentially determined by a point.
Okay.
In this toric skeleton. So there are various ways to see it, but yeah, I mean, it's really not that hard. It's a computation you can do very explicitly because these brains are also very explicit.
Okay, thanks.
Okay, no problem. So what I'm going to say now? So now I can talk a little bit about the exponential networks, but let me see. Yeah, so now I will talk about what's the definition of this exponential networks. So there is a kind of physical derivation of this exponential network, but unfortunately it takes that usually takes very long to explain. So let me first give you kind of a more mathematical, like a direct definition of what they are, given based on some data, and then I will try to motivate for you what is this exponential network actually, where it comes from. Okay. So the exponential network is, as I mentioned, is very similar to this spectral network, spectral networks. In the case of the spectral networks, your problem, the curves come from some hitching, kind of hitching type system on a curve C, and then the sigma that we have here, the sigma will be what you usually call the spectral curve. So in both cases, here and there, of course, there is a natural, there is a differential on these curves that we will need. So okay, let me. Okay, so the exponential network. So we start with this curve sigma on C star cross C star. Okay, and for convenience, I will denote so here X and Y. And for convenience, I need this. What the fuck? For convenience, I need here the exponential variables. Okay, I need this logarithmic variables. I will need in the following. So I'm going to denote them once and for all here. So there is a differential. There is a differential that many people here will find familiar. There is a differential on this curve, holomorphic differential, which is given by the following: log of y dx over x. Or if you want, this is y dx. So this differential, as you see, there is a big, is not same as in the case of there is something that makes it very different from the case of spectral networks, right? So in spectral networks, you have some meromorphic differential. You have like some curve that's defined some affine space, and you have some meromorphic differential. So here, in order to write this differential, you need to use this logarithmic coordinate y. That makes it the problem kind of considerably more complicated, actually. That's one of the main complications, and that's the reason why they are called exponential networks. I have to mention here then that exponential networks was actually created by, or invented, or I don't know, proposed, let's say, by originally by Iger, not by us, Iger, Selmani, and Barger in some paper from, I think, 2017. So the paper is called Exponential Network, so you can find it very easily. And I will proceed with the definition, which essentially comes from that paper. So we fix some angle theta. So some variable here. Okay. And before I need to, yeah, okay, better. First, I need to define the, for convenience, some coverings. Okay. So for convenience, I will sigma. I can take like this. So I will consider sigma has a branch cover over C star, where C star is just the C star where the coordinate x lives. I could have chosen C star of y, but you just choose one. So this is some branch cover over here, and I will also consider some logarithmic cover of sigma. One is like this. So in here, so here the coordinates. So just for you to be more concrete. So the coordinates here are this, and the coordinate here, right, so I can write it like this if you want, where J is 1 to R is some trivialization of the covering. So it's a trivialization of this cover. Okay, so you see, so over C star, you have several branches, etc. So these branches are J, J plus 1, etc. That's what I mean by this J here. Okay. Here, the coordinates on this sigma tilde, this is like the logarithmic covering. So I will denote it like this. Where n belongs to Z. So there is infinite number of sheets here for this pi tilde, right? Because it's the logarithmic covering. So that's the idea. I mean, that's how we work. I mean, that's the type of variable we work. Maybe there are some more convenient choice of variables. Some people may differ, but this is what we found for us the best way to do the computations. So okay, so now that I define those variables and those covers, I can talk about now I can talk about the exponential network. So so now we can fix an angle theta, so meaning just some number here, and we consider the trajectories in sigma tilde defined by the differential equation log of y of j. So here again, yeah, I'm using explicitly log of y of I and too many i's. Should maybe call this k. D log of x d tau equals e to the theta. Okay, so if you're familiar with spectral networks, this equation shouldn't be a surprise to you. So tau is the parameter of the trajectory, and the trajectory, so here everything depends on tau, and remember y is a function of x because we are here on this curve. And this is essentially very similar to spectral networks, but the big difference here is that we have this thing, right? There is this this n in set that you can take any value that's parameterizing the different sigma sheets on sigma tilde. So if you want, you can think of this as a trajectory joining a point on the branch J and some like a point on the branch J and like n plus n, and a point on the branch k, in this case, comma n. So the difference is this little n. So you have many trajectories, infinite number of trajectories here of these types. So you want to solve this differential equation, but you also want some boundary conditions. So the boundary conditions that you have are very similar to these spectral networks, and the boundary conditions is when at the start of the trajectories you want this to be at the same branch and with zero n. So they are at the start of these trajectories should be at when these two, you see, these two branches coincide. So another way to say it, then let me say, so trajectories start at branch point, right? Because you have like this. Remember, so this is this point where they coincide. This is star. So this another way of saying this is that the trajectory start at branch points. So start at points where branches coincide. And we mean all the branches, including in sigma tilde, because this n is 0. Or second is that trajectories can start at intersection of two walls. So you can say, so these trajectories are called E walls, because in that's what I mean. I will do some pictures in a second. So the story, so you how, let me do some pictures. So also if you are familiar with this spectral networks, you can see how these guys look like. So the trajectories, as I mentioned, are called E-walls, and they are labeled by I, J, and N, and they have a direction. So this IJ because well, yeah, IJ here is JK, and there's N. Okay, so they are labeled by two sheets where this of this branch of the branches of sigma, where this thing moves, where this thing lives, and also this N, which is like the difference between the branches of sigma tilde. So essentially, what I will write to you now is kind of the pieces that made up this network. So exponential network is written over C star. So it's projected to C star. So in the same way that the spectral network, you project it to the base curve C. So here you project it to C star. Is made of some pieces of the following form. So I will write you kind of the pieces that you expect to find. So what happened on C star? C star X. Somehow this, yeah. What is it? I like it a little bit more, yeah, like this. Don't know why. So if you see C star X, so this two-dimensional plane, so these guys crosses usually denote branch points where two sheets coincide, and in all our examples, I have to say there's always only two sheets coinciding at a branch point, never more than two. If we have more than two, we had certain technical difficulties. But you can always do things like changing framing of your curve. Sorry if that's too technical, you can change framing to make like all the branch points to be simple, meaning only two branches comes together, not more than two. It's okay, that was just a bit of a technical commentary. So you have a branch point, and of course you have a branch cut here. And you can have, sometimes we denote it like this. You can also have punctures. You have your puncture because you have a puncture at 0 and at infinity, for instance, right? Because this is puncture plane. So you have puncture, for example, at 0, and you can have some puncture. I don't know what happened. Some puncture at infinity, for example. So more or less, this is very simple looking structure of this star. So once you have branch points, as I said, the trajectories can start at branch points, and since they are simple branch points, so only two branches come together, you can compute and you can see that here, for example, if the I and J branch comes together, there are generically three trajectories that come out of it because they have some direction, okay? You can give it some direction. This is completely analogous to the, these are the types, yeah, usually two are Ji and one is Ij. And you see n is 0, has problems for everyone, and it's 3 going out. So this is a picture you will see generally also on spectral networks. There's nothing different here. So around these branch points, this structure, it's no different. The difference starts when these guys cross. So if you have k different than j, for example, and you have a trajectory and another trajectory, so let's say this is type ijm, and this is of type jk. I think I call this n, you can see, yeah. So this is just continuation of this trajectory, jk, m, no, n. Yeah. So when these two guys cross, there can be someone. Some guy can be born here. They can have a baby there. And this is of type ik m plus n. This is also kind of a simple computation if you want, just by writing diagrams. You can do it without doing any computation, just by writing diagrams. It's a good exercise for you. You can check that there is this guy here, and there's only a unique guy that comes out of this trajectory. So the main difference is when k equals to j. So when k equals to j, when you have trajectories of this type, n, and here, then j, I, n, m, okay. So usually if you were doing this, the ordinary thing, these trajectories will just go one over each other completely uneventful. That's that's what will happen on spectral networks as well, because essentially if this is the situation, there will be trajectories. The trajectory that comes out will have to satisfy this equation with j equals k. So if you are doing spectral networks, there is no this term. So if j equals k, this is 0, and you have like 0 equal this this thing on this side, and you cannot satisfy that equation. So there's no solution. There's nothing that can be born from these two type of trajectories. But here it's not the case because you have n, so you can actually solve the equation, and you don't get one, but you get a plethora of them. So you get infinite ones of type ij, something, something. So these are infinite families of type ij, of type ii, something, something. This is the integer that, this here is the integer that will change. It's an infinite family of each of this type of ij, ii, jj. And well, I should write maybe some extra to write some ji also with some stuff there. Why are you in that computer? And so then this is the main difference and the main difficulty on this exponential network. So this is kind of the new type of diagram. So every time things cross that are of this type, there is an infinite number of mess going out. Okay, so that's what tells you more or less locally how the exponential network will look like and how the it will differ from the spectral from the usual spectral networks. So next, I will move on to the applications, I think. So is there any question here so far? No, okay. It seems everything was very clear, or everything was incredibly not clear. But
It's clear. It's clear.
let's hope. Let's hope for something in between. So there can be intermediate states, I hope. So let's now move. So this is So this is a network. So a network, essentially, the network will look like a huge mess, like really a huge mess. Like you cannot writing at a generic theta. So a generic theta, this will be a huge mess. So now let's move to the applications. So right. So now usually I go to the nonabelianization map that tells you how you compute the invariants, but now we are not going to do that. Because someone asked me, or many people, a few people asked me about these BPS quivers. So you will see why usually consider a little bit more interesting the non-abelianization map rather than the BPS quivers, but I can talk about that like in the informal session if someone is really interesting. So let's start with the BPS quivers. So the thing from the exponential network. So the basic thing to study, or the basic things to look at in this story is for as I said, since for if you take a generic angle, this thing is a mess. You want to, so we want to look at so-called critical angles, where trajectories, where some trajectories become double, what we call double walls. So this is a phenomenon that also in the usual networks is present, and in many other problems like about Stokes phenomena, etc. And the main point of these pictures you may see in many places, not only in this context, as I said. So you have like some walls like this. So these are the so-called E-walls. And at some angle theta minus, and then at some, and if you move at some angle theta critical, the walls become like this. They coincide. And then there may be some theta plus, where then the walls will cross each other. So this kind of full movement is important when you are talking about the non-abelianization map, but for the quivers, what's important is actually this step. The the angle, not necessarily the angle, but also the double wall itself. So the idea is that you can compute, or you can calculate the BPS quivers so to write the BPS quivers plus potential, because they have a superpotential. I mean, these are not just the quiver. You need a superpotential in order to have the full thing. We proceed in 3 steps. So what I will do is give you the 3 steps, which are will be kind of abstract, and then I will write for you 2 examples. Okay, and that probably will be the end of the talk, or not of the exponential networks, which we hope they live for very long. So, so first you have to identify what are called elementary webs, and I'm telling you this because this is a rather technical thing. I could have cheated a bit, but the elementary webs are some subset of the double walls. And just to mention, the double walls, because of them being like this, because of them being double walls, they are actually cycles in sigma. Not necessarily on sigma tilde, but in sigma. So elementary walls are some subset of them. I mean, sometimes if you go through every single double walls, you will get some that are kind of non-primitive. They are, you should discard them. You kind of have to get like the fundamentals, like they are cycles in sigma. So you get like the ones that are like some kind of basis. That's a way to put it. If you want to read more about this, actually this is not our definition. This actually is on paper by, it's on some paper by Gabella, Park, Longhi. Is a lot of people, so I hope I'm not forgetting anybody. Yamasaki, and I think that's all. The paper, I don't remember, it's like from 2017 maybe, but it's something called, what was this paper called? I don't remember. Something like BPS networks. They call like BPS networks. I mean, you can find, I think it's the only paper with all these people together. So they do something similar, some definition of these elementary webs for the spectral network case. That paper is not about exponential network, but you can do the same because it's just some statement about cycles on sigma that appear. So I don't need to go into very pesky details of the exponential network to define that. So once you identify this, these guys will become nodes of the quiver. The second is you count intersection of the elementary webs with orientation. You need to take into account the orientation of the intersection. And that gives you the arrows of the quiver. And finally, you want the superpotential. So you count bounded disks. And they also come with some orientation that gives you some overall sign, some sign in front. So each of these disks gives you a term in the superpotential. Okay, so that was the abstract way. So it's 3 steps. So now I will show you, I will write for you here 2 examples that are like the 2 simplest examples that you can have, and that should be enough, at least hopefully, for you to understand how this happens. So my favorite example is this one. It's just C3. So you know for C3, this curve is this 3-puncture sphere. This is the mirror curve of C3, so that what will be sigma. So this was heavily analyzed on the first paper of us, the one from 2008, for 2018. And if you write so now take C star X. So you have one branch point. There is only one branch point on the framing we choose, and there's two punctures, infinity and 0. So that's how it looks there. And the elementary web looks like this. Okay. So there is only one elementary web. This is the elementary web. There's only one that looks like this if you project. And you can see that these guys, if you are interested, there is this cycle can be identified. If you think of this actually has the mirror curve, you can identify this with a D0 on X. But now I'm not talking about actually that. The geometry of this cycle may be a bit complicated to see directly from this diagram. But if you are an artist, which I'm not, you can write it over the curve if you want. You can, and this will take more or less this form. So it goes like up, then down, then up, then down again, then up, and then down, and then it rejoins. So it has 3 self-intersection points. So you can write the self-intersection points here with the orientation if you want. These are these 3 self-intersection points. So this, for the people who are familiar with also with mirror symmetry, this is, I think, called Seidel's Lagrangian. And it's just this curve, okay? It's this curve going around these 3 punctures 2 times, essentially. So you have just one, so there's one elementary wave, so there's one node that corresponds to this elementary wave. So let's write, okay, here I'm going with the quiver. And there's 3 self-intersection points. So there's 3 arrows here, X, Y, Z. So this should start to look familiar. Now, if we want to write W, you can see there is one disk here, and there's other that I cannot write, but there's other analogous downstairs, right? Because bounded by these 3 points. So in other words, the potential then will be given by just the multiplication, like the cyclic multiplication of the arrows associated to each of these points. So that's why it's important to have the orientation, to take the orientation, take on account the orientation of the disk. So if you do it correctly, you should get this potential. So this is a well-known quiver and superpotential for C3, right? If you consider like a theory engineered by just this simple situation, by just this C3. So let's see my time. Okay, so since I started a little bit later, I can just write for you one more example. So another example is X equal the conifold. This is another example that you can also do. Here, if you go to C star X, you can compute and you will find you have two branch points, okay? Two branch points. The other one we had 1. Here we have 2, and we have some puncture at infinity again, some puncture at 0. You have two elementary webs, which more or less are. And you can choose the branch cut to go like this. There is many choices for the branch cut. I should mention, but since I'm not using it here, I should mention there's another cut here. There's a logarithmic cut that you should always write. That's very important for computation. Not for this one, that's why I didn't write, but because the same way I write this branch cut, you should have some kind of logarithmic cut. But the logarithmic cut doesn't matter for this computation because we are doing everything on sigma, not on sigma tilde. For the nonabelianization map, then it will become very important that you keep track of that. So here you have two elementary webs. So one will take more or less this form, and the other one, I think now I can use a different color. The other one is like this. So again, now there are two, and sigma is like a 4-punctual sphere. And you can also write these two here, and you find, you can check that they are this. There is this, and there is some other one that goes at both. It's like the opposite. It goes like this. Okay. So you see there is how many intersection points? So you have, oops, yeah. So you have four intersection points here, 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 and you have two disks, so one here and one underneath. So you expect 4 arrows, and you expect 2 terms on the superpotential, which also is the expected one for the coniform. So at the end, what you get if you put so there is some intersection here that also can be written with orientation like this, and there is some other like this, and some other like this. There's some other like this. If you want to see, okay, well, let me finish. And there's two nodes given by these two colors, and then it has this is like the expected. You will get the expected quiver here. Let's call this set W, this X and Y, and I know it's a bit too fast, but and then if you do things properly, you have the 2 terms where this sign comes from the orientation. Okay, yeah, you reproduce that, and you can. So if you are interested on this, and like also to see more careful how I wrote these arrows here, etc. So in our paper, on the second paper, the one from 2019, you can see a very careful explanation of how to write this quiver and this potential in general, provided you have this type of diagram. Like if you insist star, you write your elementary webs. Of course, getting the elementary webs can be an art. I mean, that part is not like super trivial. But once you have the elementary webs and you write it like this, you don't have to go to this 3D picture and to see all the intersections and the disks. That will be very inconvenient. So there we wrote some kind of algorithm to start from this projection of the elementary webs, and then you can write all these intersections, all these arrows, and also all these terms on the superpotential. Okay, I finished here. Thanks a lot.
Thank you very much. Any questions? If you have a question, please unmute yourself.
Should we think of these as n equal to 1 supersymmetric quivers or n equal to 2? I mean, what kind of quivers are these?
Oh, this will be
Gauge
n equal
theories.
to n equal to 2.
So the first example is then basically n equal to 4 superangles, right?
This example?
Yeah, because it's
Yeah,
like.
I guess so. Yes, yes.
Okay. Thank you.
Yeah.
By writing this quiver, can you obtain this Donaldson-Thomas invariant or whatever BPS states?
1 second. Yeah. So in this case, no, I was thinking about the previous question. Maybe I wasn't. No, I think, sorry about the previous question. No, I think you should think of this as n equal to 1.
Okay.
Quivers.
Okay, good.
General.
Good.
Sorry. Yeah.
Okay.
I got confused. Yeah.
Thank you.
Okay. Now I'm back to my senses. Okay. The Donaldson-Thomas invariants. The question about the Donaldson-Thomas invariants on this enumerative invariants. So in principle, you can compute them from the quiver, but that's not what we did.
Okay.
Actually, I will be very interested to understand more that computation on certain cases. But what we did to compute the invariants was use the so-called this story of the nonabelianization map, which I didn't have time to talk about.
I see. So the partition function resolve conic is very well known, like some dialogue, whatever.
Yeah.
So you can reproduce by using this nonabelian.
We can reproduce the numbers, like as I mentioned at the very beginning. This thing becomes smaller. But like these numbers here. These numbers here are computed directly with this nonabelianization map.
I see.
And they coincide with what you can compute by other methods. So if you want, it's an incredibly hard way to compute Kobakumar buff invariant on genus 0, because it's really difficult doing it this way. But it's kind of a checking if you want. These ones here, as I mentioned, I cannot compute them like directly because our networks doesn't see, or I have no way to write there like a D6 brain. That's a problem we haven't thought about, but we don't know how to actually solve.
Or even Kobakumar buffer is okay.
Yeah.
Excuse me. Can I ask you a question about those invariants for?
Yeah, absolutely.
That you had on the screen there. So, as I understand it, these should be like numerical Donaldson-Thomas invariants, and so they should depend on a choice of a homology class, which I guess is what beta is, for example, and
right.
Some of these other things. But what does the plus mean? Are they all? Are these all classes in the same homology, or I mean, D0, D2? I think those refer to things of different dimensions, right?
Yeah. That's right. Yeah. So this plus here, like this is just kind of in physics it means bounded state, but it's not really like.
I see.
Like a plus, yeah.
So is it like these things are indexed by multiple things?
Right. I mean, more formally. I mean, if you want, one should write them like this. If you saw.
Okay. Yeah. Thank you.
I mean, you just specify Mukai vector, right?
Yeah. That's right.
In mathematics language.
Yeah. So it's a charge. It's a charge.
Thanks.
Any questions?
Can you comment on the default brains? You said that you have something to once the copy, I have a compact for cycle.
Yeah, that's easy to comment because we don't have much. That's the story. Yeah, so the D4 brains. Well,
you can
yeah.
buy in that case.
Well, D4 brains will also be captured by diagrams like this. But they are kind of okay. So the difficulty is very technical. Like, I mean, the D4 brain will also look like some cycle here. That's not the difficulty. Like here, for example, I didn't say it, but for example, here these ones of the conifold, this one are actually D2 brains. So this red one is like a D2. And this black one is like some D2 bar bounded with a D0. This is a typical choice of basis actually for brain on the conifold. The D0 is not written here. There is a cycle corresponding to the D0, which I'm not writing here. It's actually looks much more complicated than this. But the point is, if you have D4, yes, you will have some other cycle over this picture that corresponds to the D4. The problem here, when you have the D4, is that, okay, let me first say, if you have only D2s and D0s, like you can adjust your angle such that the only bound state that you expect at that angle is like D2 with a certain number of D0s and like nothing else. In the case that you also have a D4 in the game, for a fixed angle, you usually will have you can have many different bound states. So it's a mess to distinguish what is this double wall becomes very, very difficult for the case of the where there's also a D4 in the game.
Okay.
It's just because more bound state can appear. Okay, this is another technical thing that maybe I didn't mention. This is kind of being honest, which is how you find these double walls.
Yeah.
So these double walls are essentially, you found them just like literally by plotting numerically this network at some angle where you expect this wall to appear, and try to read it from a very, very horrible picture.
Okay.
Any other questions? Okay, if not, let's thank Mauricio again.